in this lecture, we shall be starting our discussion on switching algebra and switching expressions. So, the title of this lecture is switching algebra. So, here we shall basically look at how we can represent a so called switching expression. See, switching expressions are ways in which we can express the functionality of a circuit in a mathematical way. Now, once we can express it in a mathematical way, there will be a number of ways to manipulate them, minimize them, optimize them, so that the final circuit implementation or realization will be smaller or cheaper. So, let us look into this switching algebra. We start with some basic definitions. What is a switching algebra? You see, algebra is a mathematical structure. I am not going into the formal definition of an algebra, what is an algebra, but I am mentioning the essential idea. In switching algebra, you see, switching algebra is supposed to be a mathematical formalism which we are using to express or represent the functionalities of digital circuits, gates, binary inputs and outputs 0 1. So, this is the basic formalism that we want to express in a mathematical way. This is what we refer to as switching algebra. So, what are the basic components of a switching algebra? Let us see that first. First is the numbers that we are working on 0 and 1. So, this algebra is defined on the set 0 and 1. So, everything is either 0 or 1, nothing outside that, and there are two binary operations AND and OR and one unary operation NOT. So, what is meant by a binary operation? Well, an operation is said to be binary if there are two inputs and one output. Binary means 2. If there are two inputs and one output, I call it a binary. Let us say AND, we talked about a 2 input AND gate. Suppose I have an AND operation, I have two inputs A and B and I have the output the AND A and B. This is a binary operation. Similarly, I can have OR, the OR is also a binary operation, output will be A or B. But you think of a NOT. In case of NOT, there is a single input, right? If you talk about NOT, NOT takes a single input A and it generates as output NOT of A. So, there is a single input which is called unary. Unary means 1, there is a single input. Okay? Fine. So, the AND operation, how do we represent it? This AND operation is typically represented by a dot or this symbol pointed hat. Now, let me tell you, sometimes for convenience we can also omit the dot, like we can say A dot B, which means AND of A and B. Sometimes we simply write A B. We do not write the dot, but the dot is implied. If you write A B, it means it is AND of A and B, dot is there. Okay? Fine. Similarly, we have the OR operator. Okay, AND is sometimes called the logical product, OR is sometimes called the logical sum and is denoted by the symbol plus or this reverse pointed hat. So, as I said, we can express OR as A plus B, this plus is the OR operator. NOT operation finally, it is also called complement, is denoted by single quote. Single quote means A quote, A dash means not. Okay, sometimes it is not mentioned, we also express sometimes as A bar. Bar also means not. There are various ways to represent not, or sometimes we can write this A. This also means not of A. There are various symbols which are used to express these operations. Okay. So, these all represent the same thing, not, either single quote or bar or this tilde operation before the symbol not. So, you see switching algebra consists of these few things: the numbers 0 and 1, 2 binary operators and an OR, and 1 unary operator not. So, there is nothing outside this. The basic mathematical formalism says and, OR and not, these are the 3 basic fundamental operations. Well, we talked about other kind of gates also. We talked about NAND, NOR, exclusive OR, but those are not fundamental gates, those are derived gates, you can say. And, OR, not are the basic. Okay. Now, we talked about switching algebra. Now in any algebra there is the concept of a variables. So, when you learnt algebra in your school, there you talked about the variables a plus b, a, b, c, d or x, y, z, you operate on the variables, right. So, here also whenever you define this kind of a switching algebra, you should deal with variables. Okay. These are switching variables. Like when I write something like a plus b, this a and b they denote switching variables. The point to note is that because we are talking about switching algebra, this a and b variables can only take 2 values 0 or 1, nothing outside that. And switching expression is a general definition. It is an expression consisting of switching variables, constants and operators. What does that mean? So, I can write an expression like this: a and b plus a and c naught plus 1 and b bar. You see, there are variables, there are constant, one is a constant, and operators and, or, not. These are examples of switching expressions. Now, you observe in a switching expression, basically you have nothing other than and, or and not, because these are the 3 fundamental operators, and, or and not. Well, of course, you can use some brackets or parentheses, and you can also use the constants 0 and 1 in the expression if you require. So, there can be variables, any number of variables, there can be constants and one of these 3 operators. Okay. So, the idea is very simple here, switching expression. Now, we shall be talking about a number of rules of switching expression. Now, the point to note is that suppose I give you a switching expression, how do you prove it? I say, let us say I give an expression, I say a plus a and b, I say this is equal to a. Well, how do you say that whether this is true or false, whether this is correct or this is wrong? This is a switching expression, this is a switching expression, this is a switching expression. So, and this is an equality equal to this. So, how do you prove this? You see, to prove this there can be multiple ways, but the first one is a simpler method, but more tedious, but right now we shall be talking about this only. We prove by verifying the expression for all possible values of the input variables. This is called truth table or perfect induction method of verification. Okay. See, we talked about truth tables also earlier when we looked at the different gates and, or, not. we said that I can have a truth table where I have all possible input values listed and the expected output value. That is what my truth table was. Basically, here for verification I say that let us construct the truth table. Left hand side, let us calculate and find out what will be the output values. Right hand side, similarly let us calculate the output values and see whether they match. If they match, then the two functions are the same, if the two expressions are the same, they are verified. Okay. All right. And the alternative method that we shall be learning and will be using a little later is we can use some kind of algebraic manipulation and then we try to prove. And for algebraic manipulation you need to know some basic laws of switching algebra, basic laws or basic rules. So, we shall first what we do here is that we shall look at some of these basic laws and these basic laws we shall try to verify by using perfect induction. Later on we shall be trying to apply these basic laws to use algebraic manipulation method for verifying other expressions. Okay. Step by step let us proceed. And in the examples that we have that we shall show, we shall be assuming that x, y, z they denote switching variables. Okay. Let us see basic laws of switching algebra. Let us look at them one by one. Basic identities. Basic identities are go like this: x or 1 is 1, x or 0 is 0, x and 1 is x, x and 0 is 0. You see, I said that you can prove them by the method of perfect induction. It is fairly easy. Let us look at the first one. So, if we try to construct a truth table, so here there is a single variable, okay, only x. So, x can be either 0 or x can be 1. So, I am listing two things. I am listing x plus 1 because left hand side is x plus 1. Plus is what? OR. You look at the truth table of an OR gate. For truth table of the OR gate, what was the thing? That the input is 0 and 0, output is 0, 0 and 1, output is 1, 1 and 0, output is 1, 1 and 1, also output is 1. So, here the second input is always 1, 0 and 1 the output is 1 and 1 and 1 the output is 1. So, you see that x plus 1 is always 1. So, we can always write it is equal to 1. Similarly, you can verify the others any same way. Okay. So, this is quite easy to verify like this, but you should be remembering these identities that if we OR something with 1, the value of the expression becomes 1, but if you OR something with 0, okay, here there is a small mistake, this should be x. Let us correct this out. Fine, let us correct this out. This should be x. All right, fine. This x. Okay. So, let us proceed. The next set of rule is called the idempotent law. What does idempotent law say? It says that the same variable, if we do either an OR an AND to the same variable, the value remains the same, does not change. So, again you try to construct such a truth table and see. Suppose the value of x is can be 0 or 1. Let us say the first one. What will be the x or x? 0 or 0, you recall OR gate, 0 or 0 is 0 and 1 or 1 is 1. So, you see whatever is the value of x, x plus x remains the same. If it is 0, it is 0, if it is 1, it is 1, no change. So, the right hand side will also be x. Similarly, if you do AND, you will see the same thing, 0 and 0 is 0, 1 and 1 is 1, same thing, this will also be x. Okay. These are fairly simple. Next, these are fairly obvious, but again these are some rules, because you need to have some laws or rules which you can use to derive more complex expressions. It says that the order of the variable does not matter when you take AND or. X plus y and y plus x, they are the same, x dot y, y dot x and are the same. So, here again you can very easily prove by the method of perfect induction. You can have x and y, these are the inputs, there will be 4 input combinations. You can compute x plus y and you can compute y plus x. X plus y means what? 0 plus 0 is 0, or 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. But if you do the other way around, the definition does not change, 0 or 0 is 0, 1 or 0 is again 1, 0 or 1 is again 1, 1 or 1 is again 1. You see, these two are identical. So, this is true, and for AND also you can similarly prove they are the same, right. So, these are the laws you need to remember, because later on when you do algebraic manipulation we will be using this. Next is complementation. Complementation means you take a variable and its complement, x and x bar. If you take OR, the result will be 1, if you take AND, the result will be 0. Well, this is also fairly obvious. You see, if you take a variable x, x can be 0 or 1. So, what is x dash? Not, it will be just not of this 1 and 0. So, if I take let us say x or x dash, or of this and this, 0 and 1, what will be? It will be 1, 1 or 0 also 1. You see, this is always 1, this is 1. But if you take AND, 0 and 1 is 0, 1 and 0 is also 0, both will be 0. Okay? This is complementation. And lastly, associative. Associative says that when you have more than 2 variables and you want to carry out or AND, so it does not matter that in which order in which do the OR and AND. For example, you can either take x or y first and then OR it with z, or you can do y or z first and then OR it with x. Similarly, for AND. Okay. This I suggest you can try to construct a truth table and verify this yourself using method of perfect induction. So, here there will be 3 inputs x, y and z, and you can use them to check for all possible combination whether the left hand side and right hand side are the same or not. Okay? Fine, I will leave it as an exercise for you. Some more laws. Distributive law. You see, now you are coming to slightly complex rules. Distributive law looks very similar to the algebra that we know, that we have studied in school. X and y plus z is x and y plus x and z, just like multiplication and addition we know. But the second expression is slightly different. This is not what we have studied in school, but now plus is OR and dot is AND, not addition and multiplication. X plus y dot z means x plus y dot x plus z. Let us show this one of these. Let us try to verify. X, y and z. So, x, y, z there can be 8 possible combinations. Five, 6, 7 and 8. These are the 8 possible combinations. Now, the second one, let us try to calculate the second one I am trying to do. Let me try to calculate the left hand side and the right hand side. So, you can step by step see. First we are doing y and z, then we are ORing it with x. Let us do it. Y and z, 0 and 0 is 0, OR with 0, which is 0. 0 and 1 is 0, OR with 0, again 0. 1 and 0 is 0, OR with 0, this is also 0. 1 and 1 is 1, OR with 0, 1. 0 and 0 is 0, OR 1, 1. 0 and 1 and is 0, OR with 1, anything OR with 1 is 1, this 0, OR with 1, 1 and this will also be 1 and 1. This is left hand side. Right hand you see x or y, x or z and of that, x or y 0 0, x or z 0 0, or of that is 0, not or of, end of that 0, x or y 0, x or z 1, 0 and 1 is 0, x or y 1, x or z 0 and 0, x or y 1, x or z also 1, and of it is 1, x or y 1 and 0 1, x or z also 1 and 1. This you can check, the others will also be 1. Okay. So, in this way you can verify this by the method of perfect induction, right. Similarly, the first one is easier to verify, same way you can also check this, all right. These are so called distributive laws. Then absorption law. Absorption law says if you have an expression like x plus x dot y, this will become equal to x. X dot x plus y, this will also become equal to x. You see, you can try to prove it by the method of perfect induction just like the way I have said, but you can also try it in a slightly different way. Like let us see the first one. This says x or, well, I am not writing the bracket, let's say x y, I am dropping that dot x dot y. So, what I can write, this is equal to x, well, this rule already you know, x means x and 1 plus x and y, x you can write as x and 1, and now you have already studied the associative, the distributive law. You can take x common 1 or y, and we already know 1 or y means 1, x and 1, x and 1 is x. You see, these rules we have already studied so far. By systematic application of these rules, I can prove this. This is proof using algebraic manipulation. Similarly, I can prove the next one also, same way. Like this one, for example, I can write x and x plus y, I can write x or 0 and x or y. X I can write as x or 0. Now, again you can apply that distributive law. This will be x plus 0 and y. 0 and y is 0, x or 0, this is again x, proved. Okay. This is also proved. So, just if you know how to apply these rules, in a systematic way, you can also arrive at these proofs. And there is another use, this so called useful law, it does not have a name like that. This is also quite useful in minimization. It says x plus x bar y x plus x bar y, I am not writing the bracket, equal to x plus y. Well, here also you can prove this in a number of different ways, you can try out. Well, I am just giving you a hint that how you can proceed, like x, what you can write this? This means x and 1 plus x bar y, and this 1 you can write as y or y dash. This is also a rule you have studied, y or y bar is 1 plus x bar y. You multiply this out, x y plus x y bar plus x bar y. Now, you can combine these two and you can see that whether you can reduce this. There is a way in which you can do that. Like for example, this x y you can write as x y plus x y, because there was a rule you will call x plus x equal to x. Okay. So, the anything plus anything you can replace by anything plus anything. So, now you have 4 terms. Let us combine this and this. In this two, if I take x common, it becomes y or y bar. Then let us take these two. If I take y common, it becomes x or x bar. Now, y or y bar is 1, x or x bar is also 1. So, it is x and 1 is x, y and 1 is y. So, that is the right hand side. So, you see you can again apply this rule systematically. Of course, perfect induction is fine, you can prove by perfect induction, but this is a more means algebraic or formal way of proving the thing. Okay. Let us look at a couple more rules which are little more complex. Well, again I leave it as exercise for you to prove it using the method of perfect induction. This is called consensus theorem. What is consensus theorem? Let us see. Consensus theorem says if you have an expression like this, x y, y z and x bar z in between, then what it says, this y z you can drop. This is the same as x y or x bar z. Same thing if you replace just with this and or, if you just interchange, if you have x plus y, if you have x bar plus z, you also have y plus z, this y plus z you can drop, just these two, these are equivalent. So, consistency theorem means this, if you have 3 such terms, one of the term you can straight away drop. Okay? This you can prove, try and prove. Okay? And involution is fairly simple, not of not is the same as the variable, okay? Because when you do a not of 0, not of 0 it becomes 1, if you do not again, it again becomes 0. Similarly, 1 not becomes 0, do a not again, it again becomes 1. So, these two are the same. Okay. So, actually we have seen a number of rules that you can have as the basis for carrying out algebraic manipulations and minimizations, okay? And we shall be seeing more such rules later and see that how we can use it for actually functional manipulation in various ways. Okay, with this actually we just talk a little bit about functional minimization and close today. Function minimization is something that we shall be taking up next. What function minimization says, that we have a switching expression, how we can simplify it we already know the basic laws, we saw many such laws. When I say simplify it, we want to reduce the number of terms, we also want to reduce the number of literals. Literal means this A, B, C, these are literals, B bar, these are called literals, and term is A B, A B C, B plus B bar D, there are 3 terms. So, this is an example, these 3 if you minimize it, it becomes this, because A B and A B C, if you take A B as A B 1, this is A B and A B C, and if you take A B common, it becomes 1 plus C, and 1 plus C means 1, A B and 1 is A B. Okay. So, it just becomes A B. There are other ways of transforming expressions also, this we shall be studying in our next lecture. One such very important theorem is called De Morgan's theorem, this we shall see. Okay. So, with this we come to the end of this lecture, we shall be continuing with this kind of algebraic manipulation in our next lecture also. Thank you.